Welcome Sven Chilton for this podcast. This is a podcast where I do with one of the formerly a PhD student of a nuclear engineering, now working in data science. He's now an alpha tester in deep learning.ai, a data scientist, enthusiastic technical communicator, and also a PhD from the Berkeley University. That gives me an immense pleasure to welcome him to this podcast, and thank you, Sven Chilton, for this podcast.
Oh, thank you for inviting me, Vishwas.
Yes. So let's get started with the questions which I wanted to ask you from a long time actually.
Sure.
Thank you so much. I just wanted to ask you this one question. What's the fundamental theory of everything in data science?
uh, Data science is so new that I'm not sure that we yet have anything that can be described as a grand unified theory, at least not in the same sense that it's used in physics. So for anyone listening who's unfamiliar, a grand unified theory in the physics sense attempts to find a unified description of the four fundamental forces, namely gravitation, electromagnetism, and the strong and weak nuclear forces. The current standard model of particle physics unites the latter three, so the nuclear forces and electromagnetism, into a single description. But that doesn't include gravitation. There are various attempts to include gravitation into the standard model to make a grand unified theory. Some of the more popular ones include the various forms of string theory, M theory, and supersymmetry. There are also things like loop quantum gravity. It's been quite a while since I delved into any sort of theoretical physics, so I'm not sure what the current state of the art there is. But anyway, data science is much newer. So anything that could be described as a grand unified theory or theory of everything of data science would probably constitute some sort of algorithm for which all of the algorithms we currently use are special cases or limiting cases. And yeah, perhaps such an algorithm exists, but I'm not sure anyone's even trying to pursue it at this point. There's still so much we don't know about data science. So yeah, not sure if that answers your question, but
Yeah, it
that's
answers.
basically what I've got.
I just wanted to ask you this one question. On a scale of 1 to 100, how much is the understanding of a human being on the potentials of fatalities of nuclear weapons today? Because I wanted to discuss, because of course nuclear energy is being used in a everyday life, it's being generated some way or the other, but like what's the fatality that is being understood? Because it's just been like a toy to some scientists who have just built it, but like what's it all about? What is our understanding actually?
Ooh, okay. So first, I'll need to make the disclaimer that I was very much on the fringe of the nuclear engineering department's purview when I was in grad school. I entered that department coming from a bachelor's in physics because I wanted to work on nuclear fusion. Specifically, I wanted to further my understanding of plasma physics and use that to help make nuclear fusion a cheap, sustainable, reliable energy source. So yeah, for one thing, that means I focused on fusion rather than fission. And yeah, we've long since been able to use nuclear fission to power reactors and weapons. For that matter, we can also use fusion to power weapons. We've been able to generate uncontrolled fusion reactions since 1952. Containing and sustaining the fusion reactions, on the other hand, has proven to be much harder. We're still not yet at the point where we can control and sustain a fusion reaction and use less energy to confine it than the reaction yields. I mean, we've been inching closer to it over the decades. The fusion community certainly has high hopes both for ITER, the big tokamak reactor that they're in the process of building in Cadarache, France, and for that matter, NIF, the National Ignition Facility in Livermore, California. So a tokamak, which I mentioned before, relies on magnetic fields to confine the plasma where the fusion reactions take place, whereas NIF is an inertial confinement device. But I realize I'm straying far afield of the original question. So all of this was mainly to tell you that what you're asking me is not my area of expertise, and never was, even when I was neck deep in nuclear engineering in grad school. If you'd like to talk generally about the risks associated with nuclear fission, both from power plants and weapons, well, first off, I'd be happy to refer you to people who know more about that than I do, people who actually study risk management associated with nuclear fission. More generally, I would say that overall, the risks to humanity and the environment are quite low. But I mean, that's a global average we're talking about. There have certainly been isolated cases of major disasters, such as nuclear weapons being detonated and accidents at power plants, most recently Fukushima. Now, I do think, as bad as Fukushima was, I do think there was a lot of misinformation about it in the months and even couple of years that followed. I think that a lot of people on the American side of the Pacific Ocean, for example, were far more worried about it than necessary. I mean, there's a reason that water is used as a moderator in nuclear reactions. I mean, ionizing radiation that's released by nuclear fission reactors simply won't travel as far through water as through air. I mean, water is a much denser medium. I remember once someone gave a colloquium in the nuclear engineering department at Cal. Yeah, they were saying, I mean, unfortunately, I don't remember what the specific parameters were, but yeah, he was saying if I remember correctly, that if you put the typical control rods from an industrial fission reactor into a big swimming pool that they typically use for moderation. Yeah, if you swam at the top of the pool, odds are that you wouldn't know the difference. You wouldn't be able to detect any radiation from the rods at the bottom of the pool. I mean, I still wouldn't do that just to be safe. But that was his overall point. So this is a long way of saying that the odds of any contamination from Fukushima reaching the west coast of the United States or anywhere else on the eastern side of the Pacific is pretty low. Now, granted, some contamination could travel through air. I mean, we noticed that when Chernobyl melted down. And moreover, it is possible that some fish, for example, or other sea life could absorb some of the ionizing radiation near the Fukushima reactor, and then travel to the other side of the ocean. If the ionizing radiation messed up any of those fish's genes and caused mutations, they could then pass those mutations on. There could be consequences from that. But still, I think a lot of people worried excessively about the dangers from the Fukushima meltdown.
Yeah, I just wanted to ask you this question because you have worked on three fields on plasma, nuclear, and also now as a data scientist, enthusiast in the technical community today. So now I just want to ask, what's your understanding of physics, nuclear physics, plasma physics, and AI? What does it mean to you at the end of the day?
What does each one of those things mean to me at
Yes.
the end of the day? Holy Jesus, that's a loaded question. Okay. In very simple terms, I would describe physics as the shoot. I'm having trouble finding the precise words for this. Let me take a second to
Yes.
think on it. Roughly speaking, the attempt to describe the world and universe around us, in particular, how the fundamental forces of nature manifest themselves, how inanimate objects behave when subjected to them. So nuclear physics, in turn, would be the physics of nuclei, and even smaller. Plasma physics is the physics of plasmas, which is related to nuclear physics. So for any listener who's unfamiliar, plasma in this context does not refer to a component of blood. The etymology is the same, but the two are quite different. Plasma in this context, you can think of as a fourth state of matter, basically a hot ionized gas. But because it's ionized, i.e., the atoms within it tend to be stripped of one or often all of their electrons. The collective properties of plasmas are rather different from those of ordinary gases, which are charge neutral. So yeah, some overlap there. And you wanted to you also wanted to know what I think of the meaning of artificial intelligence. Yeah, was there something in the middle that I was missing there, or
No, nothing.
Okay. So yeah, roughly speaking, artificial intelligence is the attempt to engineer artificial systems to think, learn, and adapt the way humans do.
Yeah.
So
No.
yeah, are those detailed enough answers? Would you like
Yes,
me
yes, yes.
to expound on them
No, no,
anymore?
no. It's actually good. I just wanted to ask you one thing. What's the mystery behind the plasma that is going on? Because it's the fourth state of matter at the end of the day, but it's been used as in medicine in some field because plasma
Oh,
medicine is
yes,
there.
yes, that's
There
true.
are there are things which are being built using plasma also today. What's that mystery behind the plasma?
Okay. So yeah, there are indeed applications of plasmas beyond nuclear fusion. You mentioned plasma medicine. I don't know too much about that, but my understanding is that people sometimes use it in roughly the same way that they might otherwise use radiation for surface level medical treatments. Yeah, so for example, treating skin cancers. Some other applications of plasmas, of course, include TVs. Yeah. Hell, maybe if you airplay this podcast, you'll watch this on a plasma TV somewhere. People also use plasmas to etch circuitry in silicon. I mean, I don't know enough about hardware engineering to know how everyone does it, but I realize that, or I know that it's a popular technique with some chip makers. Now, one of my best friends from graduate school is a process engineer at Lam Research. So yeah, he uses plasmas all the time to etch circuitry into chips.
What are the mysteries that are being there in the industry of plasma? Because it's never been understood in a fashion which we have understood how data scientists are at least working today. What's that mystery behind the plasma actually?
Oh boy, another loaded question, but I'll try my best to answer. So one reason for the mystery is that a lot of the equations which one typically uses to describe the physics of plasmas don't have exact solutions. Yeah, unless you're talking about some very, very simplified toy problems. But yeah, many of them are so complicated that no general solutions exist. And you would have to approximate those numerically. If you're really curious, we can get into some of the complications involved with that, of choosing the appropriate numerical scheme for solving a plasma physics problem. Yeah, in fact, that's what I ended up writing my dissertation on. So that's part of it. Another mystery of plasmas, as you put it, is something that I alluded to earlier, at least with applications to fusion energy. And that is that plasmas are very difficult to contain. So there are three ways you can contain a plasma. There's magnetic confinement, which is behind tokamaks and similar reactors. There's inertial confinement, which is what's behind NIF. So the way that works is you've got this little plastic coated pellet containing the fusion material. In the case of NIF, it's deuterium and tritium, which is most commonly used in experimental fusion reactors here on Earth. For a direct drive, which isn't really used much anymore because it's really difficult to impact on the target pellet uniformly. You would fire either laser beams or beams of heavy ions directly onto the surface of this plastic pellet. For indirect drive, that pellet is contained in a cylinder called a hohlraum, which has a whole bunch of mirrors in it. So the beams instead impact on the ends of this cylinder. That energy is converted into the X-rays. The X-rays then bounce off of the mirrors inside the cylinder. And those X-rays then impact on the surface of the pellet as uniformly as possible. The plastic pellet then ablates, and the deuterium and tritium inside compress. the resulting pressure and temperature increases then create the ideal conditions for the deuterium and tritium to fuse. And finally, there's gravitational confinement. That's what you have in our sun and any other still living star that hasn't turned into a white dwarf or a black hole or a neutron star. So yeah, for obvious reasons, we're not going to attain gravitational confinement on Earth, but inertial confinement is similar. Yeah, you just need to you just need to get that reaction going.
Yes, because you have worked on both nuclear engineering as a plasma scientist to one extent, because you have also done good amount of work from being a bachelor's in physics, master's in master's and your PhD in nuclear engineering, worked on plasma aspects, and everything is fine. But at the end of the day, I just wanted to ask you this one question: what is mathematics all about to you?
Ooh, well, that's slightly different from where I thought you were going to go. I thought you were going to ask me about how I view the difference between math and physics.
Yes, you can answer that also.
So, okay, sure. I'll try to approach the question you just asked me from that perspective. So I was saying earlier that physics is the attempt to describe how inanimate objects act under the influence of the four fundamental forces of nature. And by extension, how inanimate objects work in the world and universe around us. Now, obviously, there are crossovers between that and chemistry and biology, which describe life. But at its core, physics isn't a life science. Now, mathematics is a language that we typically use to make these descriptions of the forces and how objects act under their influence. The biggest difference, in my opinion, between mathematics and physics is that mathematics is more abstract. A mathematical construct then need not correspond to anything in the physical world or universe. Whereas if someone comes up with a physical theory and describes it with a particular mathematical construct, then there has to be some test done to make sure that the correspondence is valid. This is actually one of the biggest complaints that many physicists have about string theory. We currently don't have the technology to test many of string theory's predictions. And we would have to make dramatic advances in accelerator technology, or at the very least, find ways to detect the interactions that string theory talks about in the outside universe. Before we can really say that string theory is a valid physical theory. So yeah, does that answer your question?
Yes, it answers my question. But I wanted to ask you this one question because I just want you to give your view on which is the most revolutionary idea in science today.
Oh my God, yeah, that's a really hard one. Um, Most revolutionary idea in science today. Well, I'm not sure this is revolutionary. The idea has been around a long time. But perhaps the idea that one day humans will be able to upload their consciousness into machines and achieve technological singularity. I mean, I do think someday it might very well be possible. I think we're a long way off from that happening. But I mean, we keep on making advances in computer technology and in robotics. So, yeah, who knows? Maybe even within our lifetimes, we'll be able to engineer machines that really can think. And if we do that, it's not too hard to imagine that there will be an increasingly or a decreasing distinction, I should say, between human consciousness and machine consciousness.
I just wanted to ask you this one question because you have been in nuclear engineering for a long time because that was your PhD all about. But all of a sudden, it's in data science in your resume that is popping out, which is saying that I'm an alpha tester in deep learning.ai. I've been in tech. I've been in this technical community for quite a long time now. How is the journey from being a nuclear engineer to a data scientist now?
Oh yeah, that's quite a story. So first off, uh, despite the fact that my master's and PhD say nuclear engineering on them, well, actually, I guess technically they say engineering dash nuclear engineering on them. Yeah, that's simply a peculiarity of the University of California system. Uh, Despite what my degrees say, I always thought of myself as more of a scientist than an engineer. I mean, as I said before, I was very much on the fringe of the nuclear engineering department's purview. Uh, well, shoot, where was I going with this? Anyway, I'll move on from graduate school. By the time I finished my PhD, I realized that I neither wanted to become a professor nor become a staff scientist at a national lab. So my dissertation focused on numerical partial differential equations. So given that background, the most obvious thing to do seemed to be to find a job at a company making simulation software. So places like Wolfram Research, MathWorks, ComSol, ANSYS, Cadence, Autodesk. And I tried very hard to get hired at those places. But for whatever reason, at least at the time, it seemed that jobs at companies like those for people with backgrounds like mine were a lot fewer and farther between than I anticipated. Now, around this time, I noticed that many of my peers were transitioning into data science. So I thought, what's that about? So I started dipping my toes into that pool by attending this talk series on the UC Berkeley campus, The Hacker Within. Ostensibly, it was about scientific computing in general, but it quickly took on more of a data science focus. At first, I attended those talks rather sporadically, but then gradually I did so with increasing regularity. And I even ended up giving a few talks in that series myself. By that time, I was further augmenting my data science skills through a combination of workshops, online courses, and boot camps. And one of them led to the contract gig at the National Data Center, and that led to everything that's followed.
Working in those fields, coming back to and data science, a world of data science, it takes a lot and lot of transition. Of course, you have attended a lot of boot camps, you have attended a lot of uh, sessions which was being conducted outside. But I just want to give you that insight. What was that technical constraint that you faced when you were doing your initial day projects in data science today? What's the difference?
What were the Sorry, what were the technical constraints I faced when
When you
starting my training?
started? Yes.
Okay. I'm not quite sure I understand what you mean by technical constraints. Are you talking about what technical aspects of data science did I find
Yes. Yes.
challenging when I started to learn
Yes,
it?
and also there was no hardware which was being compatible to an extent where what we have to do in the data science today. There are lot and lot of open source cloud platforms which are available and all these, but what are those? That's what I really asked you.
Okay. So, yeah, if I've understood this correctly, yeah, stop me if I'm barking up the wrong tree here. Uh, some of the technical things that I, in particular, found most challenging when I began my transition into data science, yeah, include the fact that my background in statistics was rather limited. I mean, I do know a fair deal about math at this point, but my formal training in it was much more focused on calculus, differential equations, and yeah, numerical differential equations. So yeah, some of the techniques are similar, but yeah, there was also a fair bit of statistics that I had to catch up on. Also, yeah, the programming algorithms are very different. Yeah, the way you would go about building a regression system or a classification system, I mean, even something really simple, yeah, is very different from the algorithms you would use to try to solve a differential equation numerically. Yeah, although there's starting to we're starting to get some convergence there. A few weeks ago, maybe even a few months ago by now, I read this blurb on LinkedIn that some researchers have developed a neural network which solves the Navier-Stokes equations numerically. Yeah, the Navier-Stokes equations are the fundamental equations of fluid mechanics. What made this blurb particularly interesting was that the researchers whose work was cited claimed that their system was generalizable enough that you didn't need to retune it if you changed the initial conditions of the problem, yeah, which is fantastic because with other techniques one typically uses to solve a system of differential equations numerically, that's not true at all. So if you use your numerical solver to solve the system with one set of initial and boundary conditions, that you would not typically be able to use that with a different set of initial and boundary conditions. Okay, in some cases you still could, even with these older approaches, namely if that system of equations is linear. So that is if y and z both solve your system, then some real constant plus y, or sorry, some real constant times y plus some real constant times z is also a solution. But a lot of systems of differential equations out there are not linear. And if I remember correctly, the Navier-Stokes equations are one such system. But yeah, let me check on that just to be sure. All right. Okay, yes. Yeah, the Navier-Stokes equations are indeed nonlinear. All right, what did you next want to ask me?
I just wanted to ask you the chemistry behind the plasma physics which is going on. The plasma, actually. The chemistry behind the plasma. There is a huge and a humongous difference between what's our regular and then normal chemistry was being studied, and there's a huge difference between what plasma is all about. What's that actual difference between that chemical aspect which we are thinking about in terms of plasma?
Okay.
Of course, there is a hot plasma, cold plasma. There are a lot and lot of things which are coming up. But like, what's that chemistry which differs now?
Right. Let's see how best to go about answering that. So, all right. Sorry, I should have silenced my phone here. So for one thing, usually when people talk about chemistry, they're not talking about nuclear or atomic interactions. Usually when people talk about chemistry, they're talking about manipulations of chemical bonds, manipulations of the electromagnetic force. Whereas nuclear interactions involve manipulations of most particularly the strong, but sometimes the weak nuclear force. So yeah, we're talking about different fundamental forces here. Now, with plasmas, yeah, so as I mentioned before, I was interested in the fusion energy applications of plasmas. So there, you then, well, you get two small nuclei to collide and fuse into a larger nucleus. And yeah, sometimes small nuclei will also be released from this. So for example, let's take the case of deuterium-tritium fusion. So deuterium and tritium are both hydrogen isotopes, which respectively have 1 and 2 neutrons in addition to the 1 proton, which defines hydrogen. So when they fuse, they make a helium-4 nucleus. So 2 protons, 2 neutrons, and a single neutron escapes. So yeah, that is fundamentally different from a chemical reaction. For example, in getting hydrogen to bond with oxygen to make water. In that case, you've got electrons and their shells at play. You get the single electrons orbiting hydrogen nuclei to fill the remaining slots in the second electron shell in the oxygen atom. They thus form covalent bonds, and yeah, thus you get the V-shaped H2O molecule. Right, and the hydrogen atoms are pushed that way because of residual charge imbalances in the oxygen atom. Yeah, and incidentally, that is what makes water polar, and uh, thus thus renders it an oil which is nonpolar, insoluble. So a nonpolar molecule, on the other hand, will have a much more symmetric electric charge distribution. Um, right, and this polarity is what also renders water so cohesive. Yeah, I realized that was a bit of a sidetrack there.
No, no, it actually answered all my questions which I had about plasma, and I actually got the basic understanding of what is actually required in order, because you have, it's been a long time since you have touched all these subjects, but at least you answered all these with a lot of ease, because you have worked on that for quite
Yeah.
a long before. So thank you so much for this amazing podcast, sir. It was amazing talking to you. I think probably nobody from, somebody who wants to really want to change their field from anything like mathematics to the data science, I think probably this podcast will be an example for them in order to b- enter this world of data science and the world of deep learning today. Thank you so much, sir. Thank you so much for this
Oh,
amazing podcast.
you're most welcome. Uh, Now, if you want to talk more specifically about making the transition into data science, now over the last several months, I've spoken at a number of Pi and AI meetups on precisely that topic. About how to get started learning the necessary algorithms and mathematics, and how to then start putting them into practice. So yeah, I'll let you know the next time I participate in one of those things.
Sure, sir. Thank you so much. Thank you so much for this amazing podcast. And I think